Do you want to know all about the different types of chemical bonds? Well, you've come to the right place. But now, before we dive into this topic, I first want to quickly just say that if these videos have helped you in any way, please consider subscribing or liking this video, as your help pays it forward for future students. Also, if you want additional practice problems on this topic and a lot of other topics, head on over to our website at glazersguide.com. The link will be in the description below. My brother and I, we have curated a lot of questions for you so that you can ace those quizzes and exams. And we think that you will greatly benefit from performing these practice problems that may look similar to the ones on your exams or quizzes. All right, without further ado, let's dive into today's topic. Now, this discussion on the different types of chemical bonds wouldn't be made possible without one super important chemist. Probably one of the most important chemists that you're probably going to learn, and probably the only one that, is going to be used in a lot of different chapters. And this guy's name was Gilbert Lewis. So let's write that down. That's going to be the first notes that we take. Gilbert Lewis, Mr. Lewis, PhD. Now, throughout this whole course, you're going to see the word Lewis. Lewis contributed a lot of information to the chemistry that we know today. We have Lewis symbols, we have Lewis structures, we have Lewis acids, we have Lewis bases. Lewis invented the name photon and the octet rule, which we're all going to get into at some point in this wonderful chemistry journey. But, little fun fact, the chem community did this guy dirty because he was nominated 41 times for the Nobel Prize in chemistry. And can you guess how many he won? Yeah, big fat 0. Horrible. But I guess that's life. But anyway, Gilbert Lewis, right? Gilbert Lewis was basically, he was the first one that had this major breakthrough about a type of chemical bond. And what he found out was that chemical bonds, and we'll start adding to our notes, chemical bonds involve electrons being shared. So let's actually we'll say chemical bonds involve sharing of electrons. And just make a huge mental note here that this is not about the protons, this is not about the neutrons. Everything about chemical bonding is all about those good old electrons, those particles that are outside the nucleus. And Mr. Lewis found out that, in order for bonds to be made in a molecule or a compound, those electrons are going to be shared. Now, this is one specific type of bond that we're going to be seeing, but let's break it down for you, right? And what he basically depicted was the formula of probably the most simplified molecule that we can get. When we take two hydrogens together to make H2. And H2, right, hydrogen is the first element on the periodic table, which we'll see in a little bit. But in this molecule, H2, we have two hydrogens, right? So we have one hydrogen here, and we have another hydrogen here. And let's see how these guys are going to interact. Well, from our lovely periodic table, we know that each hydrogen only has one electron. And this is just as review, but let's head on over to the periodic table. Okay, so hydrogen is right up top here, right? And keep in mind that the atomic number is the number of total electrons. So in this case, hydrogen is the first element. We know that hydrogen only has one electron. Your atomic number represents the number of protons and the number of electrons, but since we're talking about bonds, nobody cares about the protons, so we're just going to say that hydrogen has one electron. Let's head on back to our notes. Okay, and we're back. we now know that each hydrogen only has one electron. So I'm going to put a big dot over here, pop up, and another big dot over here. And these hydrogen atoms are going to interact. They're going to come, they're going to come close to each other, and somehow these electrons are going to be interacting with each other. Well, how does that happen? Well, one electron comes from one hydrogen, the other one comes the other way. And it turns out that these hydrogens, they're not greedy, right? They just want to share. So I'll draw my two hydrogens here, 1, 2. And now we have our two electrons right smack on down in the middle. And that shows us that now the hydrogens get to share each other's electron. In the beginning, this hydrogen only had one electron, and I'm going to represent that by like 1e minus. Keep in mind that electrons are negative. And this hydrogen was only chilling with one electron. But now, these are sharing, right? Those electrons are right smack in the middle so that both hydrogens can share it. So this hydrogen now technically has 2 electrons. And this hydrogen also, 2 electrons. So that's cool. Now, let's just put a specific name for this type of bonding, right? So this specific bond in which we are sharing the electrons, these are called covalent bonds. And that is a specific type of chemical bond that we're going to see. So, types of chemical bonds, one is totally a covalent bond. Now, just by definition, let's just write out what a covalent bond is. And we're making this page super beautiful. Love it. Love all the colors. What do you guys think? Colors is my thing. But anyway, let's keep going. So a covalent bond is a bond. Whoop, what happened to that B? It's a bond in which we'll say 2 electrons, generally, right? We're going to see different types of covalent bonds, different types of sharing bonds, but it's a bond in which 2 electrons are shared by 2 atoms. And they could be the same atom, right? In this case, we have H and H. But could it have been different atoms? Could it have been an H and an O sharing? Sure. Could it have been an H and an F? Sure. Could it have been O and an F? Sure, right? And as we progress through this course, you're going to see tons of different types of covalent bonds. But now, let's bring out even a bigger picture. So we know that specifically that if we have sharing of electrons, that type of bond is called a covalent bond. So since this is sharing electrons, this is a covalent bond. And if you have covalent bonds, you now can say that you have a covalent molecule or a covalent compound. Covalent compound, covalent molecule. Some professors or some teachers use compound and molecule interchangeably. Just know that by definition, a molecule is when you have just the same element repeated. So in this case, H2 would be classified as a molecule, but if you had different elements, then you would call it a compound. But if you have a covalent compound or a covalent molecule, that just means that you have a compound or a molecule that only has what types of bonds? Yeah, you got it. It's a compound or a molecule that contains, and we'll say only covalent bonds. How fun is that, right? This is easy peasy. Chemistry is not hard, guys, right? If you follow us, you guys are going to be golden for your chemistry course. So now just know that we're going to be seeing a lot of different types of covalent bonds and as a whole, covalent compounds or molecules. This is specifically a covalent bond, and since it only has one covalent bond, H2 is a covalent molecule. But we're going to be seeing tons of covalent molecules or covalent compounds throughout this whole course. And it's going to be a little bit tedious writing dots all over the place. Dot, 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 dot. We don't have time for that, right? Nobody's got time for that. So instead of writing those dots all the time, a more simplified way of writing covalent bonds is by drawing a single line. So here's my H, and instead of drawing the two dots, we just draw this straight line, and that represents a covalent bond. This is a single covalent bond because you only have one line. Just know that one line represents 2 electrons. And maybe I will just say that this is a single covalent bond, and every time that you have one line, that represents that shared pair. So it's 2 electrons. Yeah? Okay. Now let's get a little bit more in depth, right? We picked the simplest element to start our discussion on different types of covalent bonds or different types of chemical bonds. Let's jack it up a little bit, right? We're cranking it up. We're on the next level. Let's pick another molecule, right? Which means that we're only allowed to use the same element, but instead of H2, maybe we'll pick F2. Okay. And let's see what's going on there. Now, from, I guess this would be a little bit of a review, but maybe I'll post it up here. That just know that bonding, and can I say, yeah, we could make this as a definite. Just know that covalent bonding, and maybe I'll extend it from this, right? Covalent bonds is a bond in which 2 electrons are shared by, the 2 atoms. This can only occur with only valence electrons. So valence electrons are a concept that you've probably learned when you did your electron configuration, 1s, 2s, which we'll touch upon a little bit briefly here. But valence electrons are the outermost electrons. Okay, so we know that F2 can only make a chemical bond in which it only can use its valent electrons. So maybe what we'll do is I'll just write out the electron configuration for F2, right? And once again, this is a review. So if you want, you could pause the video and tell me what the electron configuration is for fluorine. 1s2, 2s2, 2p5. And keep in mind that all of your total numbers on the top, so that's totally color clashing. The 2, no, that's color clashing. The 2, and the 5, this should all make up the total number of electrons. 5 plus 2 plus 2 is a total of 9 electrons, and that's how many fluorine has. However, we can only make bondings with valence electrons. These are your total electrons, but how many valence does fluorine have? Yeah, it's got a total of 7 valence electrons. Now, some of you might be saying, wait, where'd that come from, right? There's 2 different ways to think about this. Keep in mind that your valence electrons are going to be the highest principal number. So the big 2s, I got 2 of these and 5 of these. 2 plus 5 is a total of 7. But there's an even easier way, and I'll show you on the periodic table. So let's go. Here we are, a beautiful periodic table that we will explain, but I told you you would see this guy's name. Here he is, Lewis dot symbols. But we're talking about valence electrons, so let's not just jump the gun, right? Keep in mind that for your representative elements, which are basically your 1 group, your 2 group, and your basically all your A's. So 1A, 2A, 3A, 4A, 5A, 6A, 7A, and 8A. your valence electrons are going to be your group number. So let's write that down. So your valence electrons, aka, remember the valence electrons are your outermost electrons. These are going to be the group number. But remember that it is not for all of the elements. It's going to be the group number, but only for those representative elements, which are all the ones that I have given you in green. So here's fluorine. We're talking about fluorine, right? Fluorine is right on top over here. And fluorine is part of group 7A. Now, when we talk about the valence electrons, we do not talk about the bigger numbers. You might see these numbers on your periodic table, but the valence electrons are your group number. It's the A version. Okay? So 7A. 7 is the valence electrons. I'm just going to say val, E minus, valence electrons. And if we count the dots, remember the dots, Mr. Lewis, dotting them all up, dot, 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 dot. Those are your valence electrons. And look, 1, 2, 3, 4, 5, 6, 7. So this is a good representation, a good periodic table to remember the similarities. Is that, take your time. You could pause the video and see that for all these representative elements, you have the same amount of dots as your group number. So like boron, there's 3 dots here because it has 3 valence electrons, 3A. Carbon has 4 dots, 4 valence electrons, 4A. But we're focusing solely on fluorine right now. So we're going to say 7 electrons. Let's draw in those dots. Okay, so here we are. I have 1 fluorine. Here's my other fluorine. And I'm going to draw in those dots. So each one of them had 7. 1, 2, 3. Oh, what kind of dot was that? 1, 2, 3, 4, 5, 6, 7. And as you're doing this now, you can kind of see how, tedious drawing dots all over the places. And that's why we use the lines when they come together. And notice how we want to make that covalent bond like we did for the hydrogen. We want to share 1 electron. So here's 1 electron from the fluorine. And here's another electron from the other fluorine. Those are going to share and interact. So here we go. We got 1 fluorine. Ooh, we got 1 fluorine. We got another fluorine. Sorry, guys. I'm stuck in a fluorine loop. The F's just have to be just right. Okay. So I'm going to draw those dots. 1, 2, 3, 4, 5, 6, right? These didn't get touched. Nothing, those dots didn't get touched. The only ones that got touched were these grouped ones. So I'm just going to draw them maybe in the middle. And then we will have them come together. So now this fluorine is sharing those electrons with that fluorine. So before, this fluorine had 7 electrons. This fluorine had 7. But now, since they have access to each other's electron, this fluorine now has a total of 8. 2, 4, 2, 4, 2, 4, 6, 8 dots I see. So this would be 8 electrons that this fluorine now has, and this fluorine also has 8 electrons. And if we wanted to draw out the representation, like we would with the line, here's this fluorine, here's this fluorine, a single line means 2 electrons being shared. And there's that line. All of these dots were not touched, so I'm just going to keep them. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay. Okay, now once again, if we just analyze what went down here, right, we had a single covalent bond. This bond was formed because there were sharing of electrons. Sharing is caring. So we have a single, because literally it's one line, covalent bond. And we did say that if you have just covalent bonds, the whole entire compound or molecule would be classified as covalent. So since the fluorines come together, they shared those two electrons, F2 would be also covalent. It would be a covalent molecule, just like H2. Now, just notice the difference between the hydrogen example and the fluorine is that the fluorine has these extra dots. There were no dots in the hydrogen example. So the dots are just called lone pairs. Lone pairs of what? You got it. Lone pairs of electrons. So these, maybe I'll, because I have some room here, we'll say these, and the same thing for the fluorine on the other side. These are called lone pairs. Just in parentheses, it's lone pairs of electrons, E minus, electrons are negative, but you could generally just say that these are lone pairs. So I'll put over here that each fluorine has 3 lone pairs. So each one has a single covalent bond, right? The sharing of the 2 electrons, and they each have 3 lone pairs. We group 2 electrons as one pair. So here's my first pair, my second pair, and my third pair for both of the fluorines. All right, how are you guys doing so far? I hope this is easy for you guys to comprehend. And if you have any questions, just leave them down in the description. All right, but remember to do some practice problems. But we got more to discuss, right? So let's go to a brand new page and let's continue on. I'm excited. This is super fun. Let's go. Okay, so I just brought over some of the most important stuff that we have described already, aka what is a covalent bond? Keep in mind that it's shared electrons, and if you only have covalent bonds in a single compound or a molecule, your whole entire molecule or compound would be classified as covalent. So I have 2 covalent molecules that we have discussed, H2 and F2. Now, just know that the structures that we just drew, without even knowing, we have drawn successful Lewis structures. See? There's that name again. I told you, Gilbert, Mr. Gilbert Lewis coming in hot. So just know that these 2 are Lewis structures. And maybe what I'll do is there we go. So we have successfully drawn 2 Lewis structures, and we didn't even know it, right? A Lewis structure can only be used for covalent compounds or covalent molecules. So I'll just say covalent comp, covalent molecule. And it's the representation that we draw lines for the shared electrons and the lone pairs as those dots, the unshared electrons, right? If you just draw dots, that means that the other fluorine can't get access to them. So we have lines that represent the shared electrons. The dots are the lone pairs. Okay, ready to crank it up another notch? Let's go for it. We're having fun. So we did the most elemental Lewis structure. Check. We did a structure in which we had dots. Check. Now, let's do a Lewis structure that has different elements. I like it. And I guess let's pick the substance that we need to survive on this earth. You got it. Water. Right? It all comes back to water. So, we're talking about good old H2O. Okay. So, let's see. How are we going to write this Lewis structure? Well, keep in mind that it all comes from the valence electrons. And we just saw a little trick, right? We got to know from that chart the valence electrons. And remember, the valence electrons are always the group number. So I'm just going to write down, okay, I need to know hydrogen's valence electrons, and I need to know oxygen's. Now, we already discussed how many electrons hydrogen has, right? How many? That's exactly correct. One electron, right? Hydrogen only has one electron. So that one electron has got to be the outermost electron. But now we just got to figure out how many does oxygen have. Let's head on over to the periodic table to see how many valence electrons. And if you want, pause the video. If you've got a periodic table in front of you, pause the video. Tell me. Shout it out at the screen. I might not be able to hear you, but we'll see if you got it right. So let's head on over. Here we are, back to the valence electrons, the Lewis dot symbols. Where is oxygen? Oxygen is fluorine's best friend. They're right next to each other. And oxygen is in group 6A. Keep in mind that the valence electrons are only the A group. So, oxygen is in group 6A. If you said that oxygen had 6 valence electrons, you are absolutely correct. And this is the most general way that the electrons are going to be dispersed. That you would have 2 pairs, right? Or you could say 2 lone pairs, right? The dots. And then you have these single electrons. And if we count the total dots, we get a total of 6. And just to put it, just to kind of show you, right? It wasn't a coincidence that when, I made this for you guys, that I put them in the fashion that the lone pairs are lone pairs. Those aren't the electrons that are going to be sharing. The one electron is the shared one. So you can kind of memorize how these look, and you can determine who's going to be a shared electron and who's going to be just a lone pair. Anytime that you see that you have a lone pair, the 2 dots, next to each other, those aren't going to usually have the bonds. All right? But let's head on over. We now know that oxygen has 6 valence electrons. And let's use that to our advantage when we do water. So let's go back. Okay, so oxygen, 6 valence electrons. Maybe we'll keep them the same. Okay. Now, we've seen before with the hydrogen, right? Hydrogen, when bound, it can only make one bond, right? Hydrogen does not have an extra electron on the other side to bind again. So hydrogen, when it's bound, is only going to want to form one bond. Now, we're going to get into the specifics of how to draw Lewis structures in later topics, so hang on tight for that. But just know that for H2O, since hydrogen can only make one bond, it's got to be on the outer side of, or the outside of the structure. So in this case, we're going to have beautiful oxygen in the middle, surrounded by 2 hydrogens, one on each side. And just like we said before, right, we only take the valence electrons. Hydrogen had 1, so I'm going to put the 1 dot here, boop, boop. And oxygen had a total of 6. We had 1 on the left, 1 on the right, that pair on the top, and the pair on the bottom. Can you see the sharing? I think you can, right? Let's now draw what this would be when it gets shared, right? Which means that the 1 electron from the hydrogen is going to share with 1 electron from the oxygen. 1 electron from the oxygen is going to share with 1 electron from the hydrogen, right? They're going to come as close together as possible. So I'm just going to draw the oxygen again. And maybe I'll do 1 like up here. 1, 2, 3, 4, 5, 6. And then I'm going to draw my hydrogen, H and H. And now comes hydrogen's electron. There we go. And looky there. Now we have shared electrons. But we don't like to draw like that, right? We like to draw it as the lines. So what I'm going to do is we're just going to say, we're going to go like this, and then we're going to go like this, and they all are basically together, right? So oxygen in the middle, surrounded by the hydrogens. The oxygen had the two lone pairs, one on the top, one on the bottom, and then we'll just make a beautiful bond. We'll make this purple or whatever to show the shared electrons. Okay? And, let's see, what was I gonna say? Just to, reinforce that oxygen now has two lone pairs, right? And two bonds. Two lone pairs of electrons. They are unbound, right? They are not bonded. And it has two covalent bonds. And each hydrogen has one covalent bond. Okay. Now let's just take the water. So I'm just going to redraw it here quick. So we have H, and I'm not really concerned about the coloring. Just making it pretty, right? But now we know that we got two bonds and two lone pairs. Okay. And what I'm going to do is I'm just going to say how many total electrons each has. This hydrogen now has two electrons because remember, it's sharing the other electron with the oxygen. And at the beginning, that hydrogen only had one electron. Same thing for the other hydrogen. The hydrogen on the right had one electron, and now it has two because it has access to the oxygen's other dot. In the beginning, oxygen had six valence electrons, but now since it's able to share, right, it has a total of 8. And I'm going through this, I'll put this over here. I'm going through this because we just successfully drew another Lewis structure. So right now we've had a total of 3 Lewis structures. Let's get it, right? Get in. I love that saying. And I wish I was British to say it, right? I just love that saying, get in. But anyway, I guess our equivalent is yay. But anyway, so we have successfully did another Lewis structure, but I want to just discuss something further. Now, just know, the question is why, right? Why are these structures like this, right? Specifically, we could talk about the F2 and the H2O. Now, for the F2, keep in mind that, we said it before, that this fluorine, once it was all bound, had a total of 8 electrons, and this fluorine also had a total of 8. This hydrogen had a total of 2 electrons. This hydrogen had a total of 2. It seems like hydrogen, no matter who it is, wants to have 2 electrons at the end of the day. But for our other elements, what's the lucky number? Yeah, you got it. The lucky number is 8. And just know that for fluorine and for oxygen, they have instead 8 quote-unquote valence electrons, right? With sharing of these electrons, they're able to obtain the noble gas configuration. And everybody wants to be noble. That's group 8A or 18 on the periodic table. So, there's a reason for this, right? Noble gases are chill, right? Like neon doesn't even make a bond, right? Because it's so chill, it's so by itself. And hydrogen, having 2 electrons, is helium, which is also, in the noble gas category. So those are chill. That's who these atoms want to be. They want to be a noble gas. So that's the reason for this, is that when you form a covalent bond and you have a covalent compound or a molecule, you are finally able So maybe we'll say when bound, and yeah, we'll make it general. When bound, atoms will obtain a noble gas configuration. And they love it, right? Those are like their idols. They want to be like neon. They're like, ugh, I wish if only I could be like neon or argon or helium configuration. But they found a way in which they can. They have to bind. So when they make those covalent compounds, they can form into, or they can get a noble gas configuration. And it's all good. It's all good. Okay. Let's just quickly go into the rule, because it's chemistry, right? They got rules, they got names, they got everything. So, obtaining the noble gas configuration, keep in mind that generally it's going to be the number 8, is the octet rule. Oct is 8. So when we talk about the octet rule, we talk about 8 general electrons, right? And that's just basically when we have atoms, excluding hydrogen, and there's also other elements as well. We will talk about those exclusions later. But generally, an octet rule basically states that an atom, when it forms bonds, it wants to be surrounded by 8 valence electrons. So the octet rule is an atom other than, I guess we'll say other than hydrogen, and boron and aluminum. Now, boron and aluminum, they could get 8, but for now, let's just put it out there, because we're only dealing with hydrogens and other elements. An atom other than hydrogen. An atom other than hydrogen tends to form bonds to get 8 valence electrons. But I'm going to put a big hot flash here. There are exceptions to the rule, which when we start doing like Lewis structures, we'll totally get more in depth into the specific octet rule. But, we're just getting our feet wet here. Haven't really seen too many exceptions other than the hydrogen. But it does reach noble gas configuration because it turns into helium. So that idea will always be the same. Now just know that the octet rule, the 8 electron rule, the 8 valence electron rule, generally works for elements in the second period. Keep in mind on the periodic table, groups go up and down. Periods go left to right. So for elements that are in the second period, usually, the octet rule is going to be supreme. Oxygen is in the second period. Fluorine is in the second period. Nitrogen is in the second period, and carbon. So generally, when you see carbon, nitrogen, oxygen, and fluorine, once again, there are exceptions. There's boron in there, capital B, but that's an exception. But all of these, for right now, they want to have 8 valence electrons. They want to have the noble gas configuration of neon. Okay. Any questions? Can't hear you. But I know you guys are doing great out there, right? So, let's start a new page and let's just keep it rolling. I'm having so much fun. We're getting into the nitty-gritty here. We're getting into it. Now we're going to be looking at just different compounds. So this will kind of be cool. All right, so let's go. Okay, so we're talking about different types of chemical bonds, and we said that one of them that we've been talking about is covalent. Keep in mind that any time that you have sharing of electrons, that is a covalent bond. The whole entire molecule would be classified as covalent. But now let's just see different types of covalent bonds. Now, we've seen only one of them, and that was the single bond, right? So just to reiterate, we'll put down, I don't know, I guess I'll put down the water. I'm not going to really color code this as much anymore because we're getting into more advanced topics. So I'm just going to draw it cutesy like this. Beautiful. ... Okay. Oh boy. Okay. So in water, right, we have sharing of electrons. I see that by the line. And just know that these are single bonds. Okay, so we could have covalent bonds that are classified as single covalent bonds. And just know, it should be all in one line, right? Maybe I'll just say single bonds because we are in the realm of covalent. So we got single bonds, which is representative by one line. Each line has a total of 2 electrons that are being shared. So a single bond is when you have the 2 atoms that are being held by 2 electrons or 1 pair. Okay, but now there's tons of compounds out there. We are just really, really complex covalent compounds. Can you believe that? That's basically what we are. I mean, majority of what we are made up of, we're just chemical compounds. And if we are chemical compounds, what type of bonds do we have? That's right, we got covalent bonds. And our types of covalent bonds, covalent compounds, are much more complex than just a simple water. So there's other different types of covalent bonds. We got single bonds for just one line, but you also got multiple bonds as well. Now, when we do our Lewis structure topic, I will definitely in depth go over how to draw these compounds. But for this lecture and for this lesson or this session or whatever you want to call this, right? We're just hanging out, right? We're just hanging out. For this discussion, I'm just going to post up some different types of bonds. But just know that we do not have to know how we got here just yet. I will definitely cover that all in depth in the Lewis structure discussion. But let's, keep it in context of, I want to say chemistry, but duh. I guess a little bit biology, right? Anatomy, physiology, right? Water, obviously we need this for our cytosol. Cytosol, the part of the cell, 75% of the cell has to be in water, right? That's why we always got to stay hydrated. Drink your water. Also, oxygen comes in, but we blow out carbon dioxide. And if I just look at what the structure of carbon dioxide looks like, we have 2 oxygens, 1 and 2, on the outside of a carbon. And in this case, we have now not a single bond, right? Can you tell me what types of these bonds are as I'm filling in the dots for the oxygen? Bop, 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 bop. Did you say a double bond? You are absolutely correct. So this is a double bond. So we got double bonds going on, right? Single bonds, just know that it's representative of 2 electrons. Double bonds is when you have a double line. Can you tell me how many total electrons that is? Yeah, 4 electrons, right? Simple stuff. So now in this case, oxygen and carbon are sharing 4 electrons. And this carbon and oxygen are sharing 4 electrons. And if we just count up the total number of electrons now, this oxygen has 2, 4, 6, 8. When you're doing your counting, especially for Lewis structures, just get in the habit of counting by twos. So don't sit there and say 1, 2, 3, 4, 5. No. We only count by twos when we're dealing with Lewis structures. I promise you it will help you out in the long run. Same thing for this oxygen. 2, 4, 6, 8 total electrons. 8's the lucky number. Remember, that's the noble gas configuration. And the same thing for this carbon. 2, 4, 6, 8. So everybody here has 8 electrons because they are sharing. Perfect. The whole thing is like one huge noble gas configuration and everybody is chill. Let's do another example, right? We can have, maybe we'll have carbons here. They're too far away. No. We have H. No. Probably like Christina. Come on. I know. H, 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 and H. And let's do those bonds. Up, up. So now I'm showing you that you can have different types of bonds in the same structure, right? So you can have single and double bonds together. I have a double bond here. And all of the hydrogen and carbon bonds, those are all singles. So single. So you could have multiple. And if we counted up the total electrons, which you totally can, would you think that they would be the 2 and 8 electrons? They sure will, right? Each hydrogen only has that one bond, and remember, one line is 2 electrons. So hydrogen's chilling, and this carbon, 2, 4, 6, 8. There's that 8 again, and you can do it again for the other one as well if you want. And just know that, sometimes you'll have lone pairs, like for H2O, in carbon dioxide, you do have lone pairs. In ethylene, which is this cute little compound, right? It's a gas. You don't have to have any lone pairs. So it's just the way that, the compound is. Let's jack it up a little bit, right? Let's talk about another gas that is in the atmosphere. So we got oxygen gas, O2, got carbon dioxide, CO2. We have N2, which is nitrogen gas. And it's a molecule because it's just nitrogen. There's my 2 nitrogens. Remember that we do not have to really know to the extent of 100% how we got these. The only thing that we're doing right now is just observing the different types of bonds and seeing if they have the octet. And in this case, we have, we'll say, a lone pair. 1, 2, 3. Ooh. So, let's jack it up, right? We got single bonds. We got double bonds. What's this? That's right. You got triple bond. Triple bond. And if we do just the octet idea, right? Remember that, and even before we do that, how many electrons is in a triple bond? Well, each line, remember, is 2. And always count by 2s. Just get into the habit. 2, 4, 6. Let's go. 6 electrons for a triple bond. And each nitrogen is sharing that triple bond. So this nitrogen, 2, 4, 6, 8 from the lone pair. So it's got a total of 8 valence electrons. The same thing for this nitrogen again. So we're seeing that the octet rule runs supreme, that when you're making these covalent compounds, and these are all covalent compounds, by the way, because A, they all have bonds, they all have Lewis structures, and they all are sharing electrons. So yes, just fix that up. Maybe I'll just bring this down a little bit, you know, just to not confuse you what's going on here. Wee. Okay, beautiful. Okay, let's do maybe one other one just to show you. And let's do carbon, right? So we got 2 carbons. We'll do acetylene. If you're taking organic chemistry, you will fall in love. Well, because you'll fall in love with it because A, we got you covered. And B, Orgo is just so much fun. I promise. I promise it is. So let's just put these 2 together. And single bond. Triple bond. Ooh, what happened to that one? And a single bond. And start noticing, you know, some of the similarities, right? This hydrogen in here only had a single bond. This hydrogen in ethylene only has a single bond. This hydrogen in acetylene only has a single bond. So, once again, we're just showing you that, you know, you can have multiple bonds in a compound. We have a triple bond, and we also have 2 single bonds as well. And, you know, you can check the octet rule as well. This hydrogen has 2 electrons. It's helium. It's chilling. Same thing with this hydrogen. It has the helium configuration. It's chilling. And each carbon, 2, 4, 6, 8. That's cool. Oh, sorry. My nephew. He's in the phase of, that's cool. Everything. That's cool. Ugh, my gosh. Anyway, 8 electrons. Let's get it. Okay. Let's see. What else is there to talk about for this? And maybe we'll just move on to the next topic. We'll just put a little divider here just so that we don't get confused. I do hate that, you know, this guy's missing. Oh, that was pretty cool. You learn something new every day. But we don't have time for that, right? We gotta move on. Now, let's talk about, maybe, let's see. Oh, actually, I do want to mention something. Just know that, because this is going to come up big time in organic, biochem, general chem, right? When you do your Lewis structures, take note of the carbons, right? Whenever we have 3 examples now that we saw with carbon. Here's the question from me to you. When we have Lewis structures for carbon, does carbon have any lone pairs? Does specifically the carbon atoms, do they have any lone pairs? The answer is no. There could be lone pairs of electrons on other atoms, but for carbon, there is no example here in which the carbon has any lone pairs, aka you'll see dots up here. Now, like 99% of the time, right? Of course, there are exceptions. That if you have a stable molecule, if you have a stable carbon molecule, or, you know, a carbon compound, if it's stable, aka it has no charge, that carbon molecule will have zero, no lone pairs on carbon. There is an exception. It is carbon monoxide. So CO, right? Very, very volatile gas. So I wouldn't even consider it as, you know, stable. But, you know, we'll talk about that in later date. But just know that stable carbon compounds, which just means that the carbon has to have no charge on it, no charge on carbon, you know that that carbon is not going to have any lone pairs. So that's good. Okay, now let's just talk a little bit more about these bonds, right? And we have listed out that these are all covalent bonds. So maybe I'll just put that here. Covalent bonds, we have discussed 3 different types. We have discussed the single bond. We have discussed the double bond. And we have discussed the triple bond. That is the end of the road. There is no quadruple bond. There is nothing less than a single bond. So you either have 1 line, 2 lines, and 3 lines for your covalent bonds. Now, just know that in general, the bond length, and what I mean by bond length is how long these lines are. And usually with theory, your teacher or professor will like to ask about bond lengths. Now, by definition, a bond length is, if I just, draw, I don't know, maybe we'll say, here's my hydrogen and here's my fluorine. Let's just put in a new compound here. Here's hydrogen and here's fluorine. Now, obviously, they are different sizes in real life, but just know that a bond length is from the nuclei of one atom to the nucleus of one atom to the nucleus of the other. So it's between the nuclei. And so keep in mind that all these bonds, whether you have a single, double, triple, whatever it is, right, that it's from the nuclei of the oxygen to the nucleus of the oxygen to the nucleus of the carbon. And they call that a bond length. It's measured in picometers, so we're talking about super, super, super small stuff. And it turns out that the more bonds that you collect, the shorter and shorter and shorter the bond is. So maybe if we went from smallest to greatest, because usually we think about it that way, I'm just going to swap these two guys. Because the more bonds that you collect, the shorter the bond. So a triple bond would be the smallest, then the double, then the single. Keep in mind that the alligator always chomps on, here's the alligator's teeth, chomps on the bigger guy. So the triple bond is the smallest, and the single bond is the largest bond. Usually some teachers or professors like to give ranking types of questions. So that's cool. Now just also know that the shorter, smaller bonds are generally more stable than the longer counterparts. So I'm just going to write that also here, that the more bonds you have, the smaller the bond, right? The shorter the bond. And then the more stable the bond is. Generally speaking, if you have single bonds, those are the biggest bonds, right? They're going to be, I guess, less stable. And stability in chemistry means reactivity, right? If you are more stable, that means that you're not going to be as reactive, right? You could kind of think of it as like personality, right? If somebody's, stable, it's not going to be a reactive type of person. Somebody who's less stable, on the other hand, yay. But you can kind of think about it in terms of N2 versus H2O. Now, N2 is one of the gases in our atmosphere. We don't even know it's there because it's so stable. It's just chilling. It's just floating around. Nothing really gets to it. Water, on the other hand, which you're going to learn definitely in this class and in organic, in biochemistry, water reacts with a lot of stuff. So this is a really good example of single bonds, less stable, more reactive. It's got more reactions happening to it. Triple bonds, right? Sometimes double bonds, but definitely triple bonds. They're chilling, right? They're just there. They're chilling. They're stable. So that's cool. That's cool. Okay, so new page we got coming up. And now we're going to be discussing the second type of chemical bond, and then we're going to be comparing the two. So I'm excited. Let's go for it. Okay, so we have made it. Types of chemical bonds. One is the covalent bond. Dun, dun, dun. And we have stated that covalent bonds are when electrons are shared. So maybe we'll say that. It's all about sharing is caring. Electrons are shared. Sharing's caring. Everybody shares. Everybody wins. Everybody gets the noble gas configuration. The second type of chemical bond is the ionic bond. So this is something new, and we will discuss further. Now, there's got to be a difference, right? Especially with how the electrons are interacting with each other. So, in this case, electrons aren't being shared. Someone gives the electrons to the other type of atom. So in this case, for an ionic bond where you have ions, electrons are transferred. Okay. So, for this discussion, we're going to give two examples, right? I'm going to give an example of a covalent bond, and then I'm going to give an example of an ionic bond. Now, in order to give an example of a covalent bond, I'll give it in terms of a whole molecule, which we've seen, right? We've seen H2, we have N2, or we could do compounds like water. I'm just throwing some other stuff out there. Let's just do a carbon in the middle. And remember, if you have a stable carbon, it should not have any lone pairs. So I'm just going to draw my 4 lines. Because remember, 2, 4, 6, 8, that's your octet rule. And let's do chlorines on all sides. And I drew the lines, which means that I totally have a Lewis structure, and that also means that I have a covalent molecule. And these dots, right? While I'm drawing the dots, you can see if chlorine has the octet rule. And for sure it does. It has 3 lone pairs and 1 bond. 2, 4, 6, 8. On the other hand, let's just quickly draw out what an ionic bond would be. Well, I can't draw it like this because the lines are representative as sharing. But with ions, right, this is kind of a refresher, right? An ion is a charged substance. There's tons of ions, right? I mean, you have to memorize your polyatomic ions. You've seen those, right? Your nitrates, your nitrites. Let's just do my favorite condiment. What's your favorite condiment, by the way? Let me know in the comments. My favorite condiment. Without a doubt, you cannot change my mind. Good old salt. I love salt, probably a little bit too much. But salt, table salt, is NaCl. And in this case, we have sodium, right? Which is a plus charge. And the chlorine, which has the minus charge. Right? With ionic bonds, one component lost electrons and the other one gained it. The positive always means that you lost an electron. In this case, you lose 1 electron. The negative means that you gained 1 electron. Because remember, electrons are negative. So if you're more negative, you're going to have more electrons. If you're more positive, that means you lost them. You lost the negatives. Notice how the difference between how I drew these are a little bit different from covalent bonds. Now, you could also draw like brackets here if you want to. You don't have to, but it just helps you visualize the 2 ions that are going on here. we have two ions. We have the sodium ion, which has no valence electrons. So the valence electron idea still stays the same. And the chlorine has the octet 2, 4, 6, 8. Essentially, one electron from the sodium was given to the chlorine. So maybe I'll do it like that, where this one was sodium's electron, but now it's chlorine. Chlorine was like, give me that. Give me that. Okay. So we got that going on. While I rearrange this. Cool. All right. So we're going to do CCl4, which is this compound. Once again, we don't really need to fully understand how the Lewis structure came about. That's in a different section. But we just have to see like, oh, okay, you know, I have these bonds. They're definitely covalent versus I don't see any bonds here. That's ionic. Okay. Now we're going to be talking about basically attractive forces. Now, for covalent bonds, there are two types of attractive forces. There are the forces that hold the bond together. So how we were talking about that covalent bond. There are forces that keep the chlorine and the carbon together, right? The chlorine and the carbon together. It's a force that, you know, allows them to come together. And this is called bond enthalpy, which we'll be talking about in a different topic. But just to kind of get you ready for it. So bond enthalpy is the force in which that holds these bonds together. And those are totally strong. Just know, oh, what happened there? Just know that bond enthalpy is a intramolecular force. Intramolecular force is a force that's happening within the same substance or the same molecule. That's why we're just talking about the carbon to the chlorine, it's all within the same molecule. Now let me just put this over here because the second type of attractive force is not an intramolecular force, it's a intermolecular force. So we got intramolecular forces, which is specifically called the bond enthalpy. And then for an intermolecular force, we also have those in our covalent compounds as well. Now, these international, these are forces that are existing between different substances. And this is going to play a huge part in later down the road. We'll get into that. Now, maybe what I'm going to say is let's just bring this, I guess, into a bigger picture. Keep in mind that we are talking about a overall compound. So maybe what I'll say is we'll just talk about, we'll say, I'll just cut this a little bit because I just want to make sure that, and actually, you know what I'm going to do? I'm just going to say I'm going to put it over here because I have room. So covalent bonds go with covalent compounds. And ionic bonds, what type of compounds are those? You are absolutely correct. Ionic compounds. Okay. Just to make that distinction. All right, cool. So, intermolecular forces means that you have different substances interacting with each other. Now, different just means you have to have two or more. They don't necessarily have to be different species. They just have to be different, literally not the same substance. So even if I was writing out H2, an intermolecular force would be 1 H2 interacting with another H2. So in this case, we have interactions between one CCl4 with another CCl4, right? Because remember, when you have a bottle of water, right? There's a bottle of water on my desk right now. That's not just one molecule or one compound of H2O. You got millions and millions and millions and millions of, water molecules. I mean, maybe not millions and millions and millions and millions, but a ton, a lot, right, of H2Os in that water. And if you're talking about two of the waters, that's intermolecular forces. Now, just know that in covalent compounds, these intermolecular forces, these are usually, for covalent, these are usually weak. So they're not super strong. They're generally weak. Specifically, they're definitely weaker than the bond enthalpy forces, right? It takes a lot to break up bonds. However, you can break up molecule interactions, separate a water from another water quite easily, right? So intermolecular forces are generally always weaker than the bond enthalpy ones, the ones that are intra. These are stronger. Okay. And usually, because these covalent intermolecular forces are weak, that means that they're just grooving, they're jiving, they're not really sticking together. And remember, solid, liquid, and gases, right? Solids are when those molecules are super, super, super packed together. Those intermolecular forces are tight, right? You can't break that up. Liquids are a little bit, more flowing, and gases are like all over the place. As you're going from solids to liquid to gases, intermolecular forces are going to get weaker and weaker and weaker because they're just able to fly around and act, uniquely. So just know that because of this, covalent compounds are usually going to be liquids and gases, mainly due to those weak intermolecular forces. Now, on the flip side, we have ionic bonds. These have really, really, really great attractions. We have a direct positive and a direct negative. And the famous saying is, opposites attract, oh yeah. If you have an actual positive and a negative coming in, opposites attract. These are going to stick like glue. And these are called electrostatic forces. Electrostatic forces. If you don't have positives and negatives, direct negatives, you're not really going to have electrostatic forces. But just know that electrostatic forces are super strong. And because of that, you're going to see that your ionic compounds with your ionic bonds are going to be, are going to tend to be solids. Because in that container, solids are tightly packed. And just think of any type of ionic compound, right? My favorite, sodium chloride, table salt, it's a solid, right? You sprinkle it on, it's a solid, it's all good. Yum, yum, yum. Okay. Now, what I want to do is I'm just going to, actually, I guess we'll do a new page. And we're going to start listing out all the differences that you should know between covalents and ionics. We discussed a little bit about what now ionic is. It's direct positives, direct negatives. It has to be an ion. It's got to be charged. So let's go for it. Okay, so I basically just copied down everything that we just talked about and put it on this new sheet. So we're discussing covalent compounds versus ionic compounds. Covalent compounds have covalent bonds. Ionic compounds have ionic bonds. Electrons are shared for covalent. We see those lines in the CCl4 type of idea. Electrons are transferred, direct positives and direct negatives. For our covalent compounds, there are two different types of forces. You have your bond enthalpy, which is an intramolecular force, just talking about the actual bonding in a single molecule. However, there are forces that are, interacting between multiple of the covalent compound. Intermolecular forces for covalent are generally super weak, right? There is a grade to that, which we'll get into in definitely another lecture. But as of right now, intermolecular forces, comparatively to intramolecular forces, these are very weak. So they're able to roam, the molecules are able to roam around, and that's why covalent compounds are generally liquids and gases, as opposed to the electrostatic force, which is the positive and the negative force. The opposites attract force. This is super strong, so S goes with S, super strong, super solid. With that as well, just know that for your solids, right, solids are going to have way higher melting points than liquids and gases. So we could combine that information as well. Because these guys are solids, ionic compounds are generally solids, you know that these are going to have high melting points and high boiling points. Comparatively, for your covalent compounds, since those intermolecular forces are generally weak, we got liquids and we got gases, the melting points and the boiling points are generally going to be lower than your ionic counterpoint. So lower melting point and generally a lower boiling point for covalents when compared to your ionic substances. Let's do some other characteristics that teachers love to ask about. And one of them, we already discussed about water, right? Water is the universal solvent. Everything for us lives in water. Drink your water, right? Stay hydrated. Your ionic compounds are generally going to be soluble. That means that it will break down. It will dissociate. So break down, dissociate in water, right? Usually it's called soluble in water. They have a high solubility. And once again, that's because of these charges. Direct positives and direct negatives, they have much higher attractions than something that doesn't, that's something that's not charged up. All right, so many ionic compounds with those ionic bonds are soluble in water. And because of that, when you are able to break down those ions, and now you just got Na plus and Cl minus, that's where you get your electricity from. So because you're soluble in water, you have those ions exposed, and they can conduct electricity. So ionic compounds with those ionic bonds are great conductors of electricity. I guess in water, because keep in mind that you have to dissolve, you have to break down, you have to expose those ions, right? But if somebody had a probe and they stuck it in, the table salt container, the light bulb isn't going to turn on, right? The idea is that you have to dissociate those ions, then you put the probe in it, right? So you have salt water now, and then the light bulb will go on. So just know that for your ionic compounds or your ionic bonds, they only conduct electricity in, we'll say, liquid form, not solid. So that's the idea here. Oop. conducts. No, conducts electricity in water and in its liquid form. And maybe we'll just say not solid form. Now let's add a little bit of context on the covalent side, right? So let's see, we talked about melting point, lower boiling point. Generally, now it could be, it depends, but generally, there are exceptions, but generally, covalent compounds, covalent bonds, they are insoluble in water. So they do not break down. In H2O. But I'm going to just put a little caveat here just to, show you that there are some exceptions to the rule. But of course, we will get into that in a later date. But just know that most of these are insoluble. They will not break down in water. You won't get those ions exposed. So especially for this one, like if you take CCl4 and you put it in water, you're not going to see like carbon plus and Cl minus. That bond enthalpy is like holding on for dear life. But just in general, they're insoluble in water, which means that the ions aren't going to get exposed, which means that they are not good conductors of electricity. If you conduct electricity, you need those ions exposed. And if those ions aren't exposed, then you can't conduct electricity. You got to have those charges, the positives and the negatives. So we're going to say poor conductors. You might even say non-conductors. And it doesn't matter where it's at, right? You throw it in water, you try to put the probe in it, and you try to, turn a light bulb on, not going to happen. You try to put it in its liquid state, it's not going to turn on because you're not going to get those positives and negatives direct. Poor conductors of electricity, and we'll just say in all states. Once again, there's obviously some exceptions, but this is a general trend. To just have you compare covalent bonding with covalent compounds, the Lewis structures, versus the ionic bonds and the ionic compounds. And I think this is a great comparison. So just make sure that you know the differences between ions or ionic compounds and its covalent compounds and covalent bonds. Okay, how we feeling, right? We're getting through this. There's a lot of stuff that's going on, but I know you guys are doing great. So we're going to move on to the next level, right? The next topic. We got this. And we're going to be discussing something called electronegativity. Now, before I put the word on the screen, let's just revisit one familiar covalent compound that we learned about, which was just the simple H2. So I'm bringing it back. We're bringing back H2, which, if we remember, we have two hydrogens, and they had one electron apiece. They made one covalent bond. It's a single bond. And just for this purpose, right, when we just talk about electronegativity, I like to actually draw the electrons. Only for this reason. It will make sense. Okay, so we discussed this guy, right? Now, I'm also going to be discussing another compound, and it's going to be between hydrogen and fluorine. Now, if you want, pause the video and see if you can draw the Lewis structure for fluorine. I'll give you a heads up that, it is a covalent compound. Those electrons are shared. I'll start from the bottom and then I'll make that drawing. So we have hydrogen and a fluorine. Keep in mind that they all come from valence electrons, so this will be great practice. And a hydrogen only has one electron, so it's got one valence electron. And the fluorine, it's in group 7A, right? We saw that from before. Group 7A. So it has 7 valence electrons. So I'm going to do 1, 2, 3, 4, 5, 6, and 7. So when these guys come in, they're going to form that single covalent bond. I'm just going to bring it over here. And then I'm just going to draw what it looks like on the top. So we have H, we got F, single bond, right? You could also check for the octet rule, right? Everything that we've learned, don't be afraid to pause the video, check it out. But we have the 2 electron rule for the hydrogen and the octet for fluorine. So that's all good. Okay. So we have 2 different types of covalent compounds. Maybe what I'll do is we'll just put that up there. Okay. Because now what I want to do is I want to extend this. Should have just kept them farther away. And we're going to be talking about how these electrons are shared, right? Now, in H2's case, the atoms are identical, right? It's 2 hydrogens. So when we talk about the bond length, right, or the electrons that are from one nucleus to the other, and maybe I'll do this in a different color, right? Here's like the spacing that we're allowed to have. If these atoms are completely identical, that means that these electrons have the same exact time spent between this hydrogen and this hydrogen. So it's basically right smack on in the middle. That there's no pull, there's no tug, it's the same atom, and, the electrons are split right down the middle. Whee! Right? Okay. But now, when we look at this one, when we talk about the space between those shared electrons, and keep in mind, I only care about the shared ones. I don't care about the lone pairs, right? Because those are just fluorines. But when you have now different elements, hydrogen versus fluorine, these electrons are going to not be split right down the middle. Turns out that even though they are sharing, one of them is a little narcissistic. One of them got a little narcissistic tendencies. And one of them is going to be like, well, I'll pretend that we're sharing, but I'm going to make sure that it's more closer to me. And in this case, in H and fluorine's case, right? Fluorine is the one that's like, I'll make them pretend like we're sharing, but I'm keeping those electrons more closer. That's what happens. Now, maybe, we'll put big quotation marks, narcissistic. Or narc, is that what is oh boy, how do we spell that? Nobody knows. I don't. No. We're just going to say, instead of narcissistic, we're going to say a little selfish. Right? Selfish. Fluorine's like, I'll pretend. I'll make sure that we're sharing, but I'm going to be holding it better. I'm going to hold it better for myself. It's still technically classified as shared electrons because hydrogen still has the 2, but it's just more farther away from the hydrogen than the fluorine. So, we're going to say that fluorine's a little selfish. It holds electrons closer to fluorine most of the time, or basically like all the time, right? Holds electrons, maybe I'll say holds, or we'll say shared electrons. I like that better because nobody cares about the lone pairs, but the shared electrons are closer. 2, the selfish atom. And in this case, the selfish atom is totally fluorine. But if you have the 2 of the same elements, right, nobody's going to be selfish. They're identical. So they're like, yay, we're completely fair. This one, on the other hand, Now just know that when you have atoms that are selfish, this is called a polar covalent bond. Still covalent because those electrons are still being quote-unquote shared, but one is just greedy more than the other. So this one is a polar covalent bond. So now we're getting even more specific in our types of covalent bonds. So if we do this outline again, right, one would be covalent bond, and the other one, number 2, which we saw earlier, was ionic. Now just know that when you're talking about covalent bonds, now you have 2 different types. You have polar, which are the selfish ones, and basically not polar, but we call that nonpolar. And maybe I could squish this nonpolar. But there's only one type of ionic bond. There's no, separation between any of the ionic bonds. So we got polar covalent bonds. And just know that polar, you could think of it as pull. If you have a polar covalent bond, you have a selfish guy pulling PP. PP. You have a selfish atom pulling the electrons more closer to itself. On the flip side, where you have nobody, right? Straight up and down, straight in the middle, H2, this would be classified as a non-polar covalent bond. Okay, so now we see that we have different covalent bonds. We got polar ones, the ones that have the selfish atom that's pulling those shared electrons closer to fluorine, or we have the all identical, purely nonpolar. Nonpolar means no pull. So they're all happy, everyone's just chilling, the shared electrons are chilling in the middle. But yes, so now we have nonpolar and we have polar. Now, let's just dive in a little bit deeper into the polar ones, right? So we got fluorine, we have hydrogen, we have fluorine, we have the 3 lone pairs on the fluorine that are all fluorines, and then we have our space here. It is covalent, so those electrons should be right smack in the middle, but fluorine is a little bit greedy. So just to kind of show you again the visual, fluorine's like, we'll share, but I'm going to use it most of the time. They're closer to me. I need them closer to me. I want them. That's what fluorine says. That's exactly what fluorine says. So we have HF. It's a polar covalent bond. Now let's just get into, more specifics. Polar covalent bond. Obviously, it is unequal sharing, right? It's still sharing though, right? It's not a transfer. It's not an ionic bond. It's unequal sharing of the electrons. Totally fluorine is taking full advantage. And when we say that, right, we have unequal sharing of electrons, so there's going to be a shift in the electron density, right? Density just basically means how much stuff you got in a space. So when you have your electrons straight down the middle, there's no shift in electron density because everybody's all chilling, no pull. But now, this is kind of like as if fluorine did take electrons, right? He's still sharing, but he's like, I'm trying to pretend I'm trying to pretend that those electrons are all to myself. And remember, when we gain electrons, that's a negative charge. So we have a shift in electron density. Just like, just some hot words that they like to use. Basically, if the electrons move in a bond, you shifted your electron density. And because of that, you have higher electron density around the fluorine because you've added more electrons to fluorine space. For hydrogen, you have low electron density in that general space. Now, just on the scale of things, we have our nonpolar covalent bond, where there would be no pull. And on the extreme other side, we have our ionic bonds. And remember, ionic bonds, from what we learned earlier, ionic bonds are when you have a complete transfer, right? So one atom completely gave up its electron and gave it to the other atom. Just know that a polar covalent bond is right in the middle of these two. There is a pull, right? Fluorine is pulling the electrons closer to, the atom. However, he's not taking it for himself. Hydrogen's still hanging on by a thread, but hydrogen's still hanging on. He's like, I still have those electrons. I'm still sharing them. So just know that a polar covalent bond is basically a hybrid between a completely pure nonpolar, no pull covalent bond and a nearly complete transfer of electrons. Because it just actually shows you that there is something called a pure nonpolar, no pull covalent bond, where literally, if you have identical atoms, nothing's going to happen. However, on the flip side, even though we know ionic bonds as a transfer of electrons, in reality, it is not 100% complete. So that's why polar covalent bonds are on like this hybrid spectrum that there's clearly a pull, but it is not as much as the other ionic bonds. And we'll talk later a little bit about how we can tell the difference between whether something's nonpolar, polar, or ionic. And that's what we're going to be doing basically in the next section where we discuss electronegativity. So let's go. Okay, so once again, I just put up the most important part of, stuff that we went over that are going to transfer over to here. And that's the difference or the continuum between a nonpolar covalent bond, there is no pull in those shared electrons, to a polar covalent bond. Keep in mind that you're still sharing electrons, but there is a pull. And then you have you have the ionic bond where it's the complete transfer of electrons, positive to negative. One atom lost electrons, being positive, another atom or ion gained electrons, and that's where it becomes negative. But the question is, you've probably been screaming at it. You've been screaming at the computer or your iPhone or whatever, phone, general, Android, right? No discrimination there. You've probably been saying, how do we know, right? How do we know if it's going to be polar or nonpolar or ionic, right? Well, that has everything to do with electronegativity. Okay. Now, electronegativity is a very important concept to understand. And electronegativity, by definition, we'll say that it's the ability of, an atom Atom only has one T, Christina. So it's the ability of an atom to attract electrons to itself in a chemical bond. And all bonds are accepted here. So when we're talking about attracting electrons, it could either be in a covalent bond, so it could either be electrons that are shared, or it could be an ionic bond, where what was that? Okay. It could also be an ionic bond where electrons were transferred. So we'll say ionic bond or covalent. But now, keep in mind here that if we can talk about electronegativity, the one thing that we have to make sure is that electronegativity only exists if there is a chemical bond. By definition, electronegativity, there is no electronegativity if you're just talking about lithium, or if you're just talking about sodium, or if you're just talking about, I don't know, fluorine by itself. The atom has to be in a type of chemical bond, whether it's covalent, where you draw the Lewis structure with your lines and your dots, or in a plus or minus ionic bond. So that's one thing. Electronegativity only occurs in chemical bonds. And basically, the higher the electronegativity, the higher attraction you have in that bond towards those electrons. So higher electronegativity, we'll say higher electronegativity equals higher attraction towards electrons in chemical bond for whoever the atom is, right? And, electronegativity is just a concept, right? It's not like a quantifiable type of energy value that you guys have been discussing, right? We'll touch base a little bit about ionization energy and electron affinity. But as far as electronegativity goes, it's all relative. That you can find out an element's electronegativity by comparing it to another element's electronegativity. Now, who came up with this? Don't fall into the trap. It is actually not Lewis. Lewis didn't come up with electronegativity, or else it would have been called Lewis negativity. This was our boy Pauling, right? Linus Pauling, once again, a great chemist. It's always fun to put the names to, the chemists who have come up with these concepts. So Linus Pauling is all about electronegativity. I'm just laughing because of the Lewis negativity. It totally would have been, and he would have still not have won the Nobel Prize. But anyway, that's here nor there. Definitely Linus Pauling definitely won a Nobel Prize in chemistry. I can't say specifically for sure, but I would probably suggest yes. He was a good boy. Okay, so anyway, so electronegativity can only be found in chemical bonds, whether covalent or ionic. It's a relative concept, and you don't have to know how they got these numbers, nothing like that, but we have to talk about the trend. So let's go to the periodic table, and let's talk about the electronegativity trends. Let's go. Welcome to my lovely electronegativity periodic table. Now, first thing we notice is that it is a little bit color coded, which is awesome, right? Just know that everything that is in this color is considered metals. We have the purple, and this is also a review, right? The purple are your metalloids, which means that they have both metals and non-metal properties. And then finally we have our lovely orange, which are our non-metals. And let me just see. Oh, well, oh boy. I don't know just what happened. So we're just going to flow with it, right? Help. There we go. Help is on the way, dear. Where's that from? Where is that from? I'm just going to put this down. I'm just going to put it down here. Help is on the way, dear. Help is on the way. Okay. Anyway, let me know in the comments if you know. All right, so anyway, so we have metals, metalloids, and nonpolar. Cool, Christina, get with it. Non-metals. I heard you. Okay. Now, all of the values on the bottom are your electronegativity values. Keep in mind that the top numbers are the atomic number, and as we see, electronegativity values, they're not big. They're relatively quite small. They're always going to be positive values, and it's all like a relative measure. All right? Now, the only thing is we just got to find a trend here. So there's got to be generally a low area and generally a high area. Now, on the periodic table, francium and cesium, but definitely francium, on the bottom left corner, right? We got our metals, francium, big bad boy francium, generally has low electronegativity, right? I mean, 0.7. That's like the lowest number that's on here. Can you find the highest value? Yeah, it's all the way up here, from the corner to the corner. Fluorine has the highest, and fluorine is the highest electronegative element out there. So, if we have to make a trend, negativity, it would go from the bottom left as low, and then increasing. Let's see if I could go. That's not bad. Increasing. So we got the lowest values on the bottom left and the highest values on the top right. Now just know that as a general rule of thumb, as you are going across your groups, as you're going across your periods, so going from lithium to beryllium to boron to chlorine, that's going to increase. And it kind of makes sense. 1, 1.5, 2, 2.5, 3, etc., etc. And if you're going down, it depends on, whether you want to go across and down or across and up. Just know that as you go up a group, you also increase. So that is the general trend. As opposed from iodine 2.5 to 2.8 to 3 to 4.0. So we got it going on. And this is increasing. Also, there are some elements that you see that don't have a number. So for example, helium and neon, right? And we've discussed today a little bit about helium and neon, how these are your noble gases, right? And all the elements want to have a noble configuration when they make that chemical bond. And electronegativity, by definition, you have to have a chemical bond. Helium is too chill for that. Helium is like, that person that is just like, I'm fine. Now I'm Matthew McConaughey. I'm fine. But that's helium. He's fine by himself. He doesn't want to form a chemical bond. Helium, never makes chemical bonds. So, if helium doesn't have a chemical bond, it's got no electronegativity. Same thing with neon. Neon wants to be by itself. It doesn't need a chemical bond. So, has no electronegativity. Same thing with argon. There are some noble gases that technically can also form chemical bonds, and that's why they have electronegativity. But as far as your three, helium, neon, and argon, They're noble gases. They're small, relatively small noble gases. They're chill, they're stable, they're cool. They are not going to form a bond, and therefore they have no electronegativity. Okay, so now we know the trend. Francium is the lowest, fluorine is the highest, so the two F guys. From low to high, and know that trend. Now let's go back and discuss it a little further. Okay, so let's just write down what we just found out, right? So for electronegativity, we talked about how francium was the lowest and fluorine was the highest. Which means that fluorine has the highest attraction towards those electrons in a chemical bond. This guy is the most selfish in the bond, as opposed to francium, who's the least selfish, the most selfless, the least selfish. Francium's like, take my electrons. Just take it. Just take it. Whatever. And if this was a great pair, whew, that would be one reactive type of bond going on there. Fluorine's going to take the electrons that francium has. But anyway, so just know that as we go across a periodic table, we increase in electronegativity, and we'll do it the other way that we saw, just so that you guys, know things in different ways. As you go down a group, electronegativity will decrease, because as low you go, the lower the electronegativity, the higher up you are, the higher the number. Okay, so that's that. Now, let's just bring up some other concepts that we can kind of introduce electronegativity with. So we already said that, the higher the electronegativity, the higher attraction towards electrons you have in a chemical bond. And we can kind of group this all together by also giving out different properties. So for example, if you have high electronegativity, this runs on the general property that your electronegativity is high, which means that your electron affinity is high. Now, just know that electronegativity and electron affinity are not the same thing. We've stated, throughout this whole shebang thing that we're doing, right? Electronegativity, there has to be a chemical bond. It's an attraction between, the electrons in the chemical bond. By definition, the electron affinity is just the attraction for one additional electron. Doesn't have to be in a bond. So higher electron affinity, that just means that you are picking up additional electrons easily. So basically you're turning into an ion. You're turning into a negatively charged ion. So higher electronegativity, higher affinity. And we could also make one more assumption here. High electronegativity, high electron affinity, high ionization energy. These two should be a review, right? Electron affinity and ionization energy. But just know that ionization energy is basically talking about losing electrons. So if you can pick up electrons easily, that means that you can lose them easily, right? You want to keep gaining and gaining and gaining. Energy, in terms of chemistry, makes it really hard to do something. So if you have high energy, it's super hard to do. So high ionization energy means that it's hard to lose an electron. And that kind of makes sense. If you're picking them up easily, you're not going to lose them. And your attraction, if you have a chemical bond, is going to be greatly in your favor. So hard to lose electrons. And once again, for electron affinity and ionization energy, you don't have to have that chemical bond property. That is only for electronegativity. Okay. And the only other thing that I just want to point out is that these three are all directly related. So high electronegativity, high electron affinity, high ionization energy. The only one that is indirectly related to all of these is metallic character. If you have high electronegativity, high electron affinity, high ionization energy, that means that you have relatively low metallic character. And metallic character is a fancy way for saying, are you a metal or are you a nonmetal? If you don't have metallic character, you're not metal-like. So it's as simple as that. So low metallic character, not metal-like. Who would these guys be? Yeah, these would be nonmetals. And that makes sense because we did say that fluorine has the highest electronegativity. Fluorine is a nonmetal. It's got low metallic character. So definitely know these trends. Chemistry is an intricate, beautiful tug and pull and play and whatever between theory and math. And for most of what this lecture is all about, it's more theory than mathematics. But I think we could do a little bit of math. I think so. Because now there's some teachers or some professors that don't use math to determine electronegativity, but there are that do. So I'm here to give you everything I got, right? What are we, in hour 2 of this? Maybe. I'm having a good time. I got my water, I got my coffee. If you guys need a break at all, please stop the video, take a break, fill up your water, coffee, tea, whatever you guys prefer, and then come back because I'll always be here for you guys. But we're going to be doing a little bit of math next. So let's go for it. Okay, so we're back to just this again. Our continuum. Nonpolar covalent bonds, no pull of shared electrons. Polar covalent bonds, there's a little pull, between that greedy element. And then you have that complete, in theory, complete transfer, that the pull is so great that one atom completely lost it and the other one didn't. The other one gained it. In actuality, there is no complete transfer of electrons. So it's this whole idea of a continuum, right? Whether you have no pull, everybody's happy. You got a little pull, and then you got a lot of pull, aka a transfer. So the question is, how are we going to know which one is which? Well, just know that atoms in a bond, because remember, we're still talking about bonds, atoms in a specific bond that have a huge electronegativity difference are going to be ionic bonds. So, for example, where we're bringing it back. Pop quiz, what is my favorite condiment? That's how I'll know. That's how I'll know that you guys have been listening. What is my favorite condiment? Let me know in the comments. My favorite condiment is salt. NaCl. So we have NaCl, right? Generally speaking, if we write NaCl, Na has a plus charge. It has completely lost that one electron. And chlorine completely took it, right? And I say completely because that's, in theory, it would be a complete transfer, but in actuality, it didn't really happen, not completely, but, it's just easier to think of it that way. Now, when we have a ionic bond, it's a transfer of electrons. In this case, sodium lost the one electron, and the chlorine gave it. Notice, once again, that I cannot write them as Lewis structures. Can't write the bonds because it's not covalent, it's ionic. And, hold on. We'll bring this up. Gained. Beautiful. What was I saying? I lost my train of thought. Can anyone remind me? Thank you. Sodium lost one. Chlorine gained one electron. It was a transfer of electrons. And usually, when this transfer happens, you have a electronegativity difference. And I'm introducing a new type of concept here, an electronegativity difference. Now, in theory, it's the highest that can possibly be. It is great. It is large. But in actuality, when you're talking about numbers, it's not really that high, right? Now, there's two different fields here as to what your teacher or professor may give you as the number. Usually, if you want to be safe, the electronegativity difference just has to be greater than 2.0. But there are some teachers out there that give you a spectrum, which I'm also going to give you, which is a little bit of a different number than this. So, this applies to what your professor or teacher is telling you. So generally, if you have an electronegativity difference that's greater than 2.0, you're totally those atoms are involved in an ionic bond, a transfer of electrons. And if we look at NaCl, so we have Na and Cl. Let's go to the electronegativity periodic table and grab the electronegativities of sodium and chlorine. Here we are. Sodium has a electronegativity of 0.9, and chlorine, on the other hand, which is over here, chlorine, on the other hand, has a electronegativity of 3. So 0.9 and 3. Pretty big stretch, right? And clearly one is a metal and one is a nonmetal. And before I keep, switching back and forth, 2.5, 2.2, I'm just trying to remember some of these numbers just so that when we do nonpolar, I don't have to keep going back and forth. But if you have a periodic table, you can use it in front of you. Your periodic table, you should always have a periodic table in front of you to help you out. All right, so let's go on back. 0.9, 3.0. Let's go. Okay, so sodium, 0.9, and chlorine, 3.0. Now, the electronegativity difference, just know that a difference is always subtraction. So all we have to do is just subtract these two values, right? And your electronegativity difference is always going to be the absolute value. So always just take the higher number and minus the lower number. So 3.0 minus 0.9, and that equals 2.1. Safe to say it's greater than 2. This is totally going to be an ionic bond. And remember that the larger electronegativity atom is the one that did the attracting. So chlorine was like, I want that electron. I need it. I need it from you, sodium. You need to give it to me. You need to transfer it to me. And sodium, being 0.9, is like, whatever. You got it. You got it. It's a losing battle. So sodium lost the electron. Chlorine attracted it in the chemical bond. It gained. Okay. Now, let's do the opposite, right? Now, there is something that is called a pure covalent, or we'll say a pure nonpolar covalent bond. We kind of already discussed it a little bit, right? Where if it's purely like 100% no pull, the atoms have to be identical. And we've seen that with the H and the H. It's covalent, which we will see with our numbers, which means that I will write a line, right, a Lewis structure. And from the electronegativities that I just took, right, that I remembered, hydrogen is 2.2 and 2.2. A lot of textbooks, by the way, have hydrogen being 2.1. They just recently changed the electronegativity to hydrogen as being 2.2, so go hydrogen. But either way, whether you're using 2.1 or 2.2, the context is going to be the same. So nothing's going to be a big difference, so I wouldn't even worry about that. But if we do take the electronegativity difference, obviously they're the same number. We're going to subtract them and we get a big fat 0. 0 means that there's absolutely no pull. It is purely covalent. So it's purely nonpolar. And just know that, maybe we'll say purely nonpolar covalent would have a electronegativity difference of 0. But now, once again, teacher or professor specific, there are some bonds out there that have different atoms, but yet they are deemed nonpolar. For example, H with carbon, which is basically the basis of our life. We are just one big carbon and hydrogen bond. So you're going to see a lot of carbons and hydrogens in Orgo. We have 2.2, and I believe I did say 2.5 for carbon. So same thing, right? Electronegativity difference. You take the higher number and you minus it by the lower number, and then you see what you get, right? Electronegativity is always positive. So let's go on and do it. We got 2.5 minus 2.2, which gives us, what do we get? 0.3. So there is a tiny smidgen of pull. However, it is not great enough to be classified as polar. Now, just know that on the scale of things, your nonpolar covalent bonds, you just have to have a electronegativity difference of less than 0.4. So electronegativity less than, is it this one? No, it has to be this one. Less than 0.4. So 0.3, 0.2, 0.1, those are all going to be classified as nonpolar. You do have a little bit of difference, but it's not going to, upset the bank. But now we have this idea, right? Where I now have these electronegativity differences from 0.4 to roughly around 2. Now, once again, to each his own, right? Some professors say 2, some of them say 1.8, which I've seen. So that's up to your teacher or, specifically your professor. So maybe, if they're going by the rules and you want to be specific about it, I would just know the more specific number, which is 1.8. Some teachers or professors just say, hey, memorize it as 2. They're rounding, but you shouldn't really do that. But just know that all the values from 0.4 to 1.8, that's the polar category. So we'll say electronegativity, electronegativity difference to get that pull, but still it's classified as sharing, is from 1.4 all the way to 1.8. And the one that we've seen before was H and F, right? Hydrofluoric acid, depending on whether you're, liquid or solid. Not liquid or solid, liquid or gas. Hydrogen was 2.2, and fluorine is the most electronegative of them all, 4.0. And if we just take the difference, right, 4.0 minus 2.2, we get 1 point something. Let me just write this down. 2.2. That's an 8. That's a 3, 4, 1.8. So literally, right there. So greedy. Almost ionic, but not. Okay. So this is basically the only math that we're going to be doing for this topic. So we don't have to deal with any higher level math than just a couple of little subtraction numbers. Okay. Now, I also just want to point out between, just looking at the atoms that are formed between ionics and covalents, right? Generally, because, there's our exceptions, but generally when you're talking about ionic bonds, we gave one example, sodium and chlorine. Ionic bonds generally are between metals. So the ones that have super, super, super low electronegativities and nonmetals. So, the trick is if you see that you have a metal plus a nonmetal, you're going to be in a ionic bond. However, there is exceptions to the rule. That's why sometimes it's just good to just do your electronegativity difference just to make sure. But one example to the rule that I could think of is AlCl3, where aluminum and chlorine, if you subtract the values, you're not going to be in this realm, even though aluminum is a metal and chlorine is a nonmetal. So just know the generalities, ionic bonds, metal and nonmetal, but there are some exceptions. And try this one out. Let me know what you get for the electronegativity difference for this one. On the other side, right, covalent bonds, they're going to be with nonmetals, and that is pretty much going to be set in stone. That if you have a covalent bond of some sort, and maybe I'll just put it up here just so that we don't get confused. A general covalent bond, because of those electronegativity differences where we're going from basically 0 all the way up to 1.8, you're dealing with not as great of a change. So covalent bonds are between nonmetal and a nonmetal. And I don't really think that I can see any exception to that rule. But there definitely is exceptions to ionic bonds. And, once again, there is no pure transfer of electrons. It's not 100%. I mean, it's close, but in reality, it's just a continuum in which you have no pull. There definitely is a purely nonpolar end to it, because you can get a 0 value. But for ionic bonds, it's, not complete. It's not a complete transfer. Now, guys, this has been one whirlwind of a lesson, and I hope you guys are learning a lot. We have probably one more big concept that we have to discuss when we're talking about types of chemical bonds, and that's dipole moments. So let's get a clean new page, and then we'll explore all of that. Let's go. Okay, so here we are again. I have brought up the HF compound that we have discussed, in which it is a polar covalent bond, right? The whole entire molecule is covalent because it has a covalent bond. Specifically, it has a polar covalent bond because remember when we did those electronegativities, it came out to be 1.8, which is in the realm of polar, which means that there is a pull of those shared electrons. And remember, with electronegativity, the higher the number, so in this case fluorine, that means the greater attraction. So fluorine being the highest electronegative element, that means it has the greatest attraction. So greatest attraction for those electrons in that bond. Greatest attraction for electrons, I'm just going to put E- in shared bond. And on the flip side, hydrogen being less electronegative, right? It has the lesser or I guess the least in this case, the least attraction for those electrons in the shared bond. And, if we wanted to, we could put, just to make it clear that those fluorine does have lone pairs. So I'll just put them in there. But remember, when we're talking about bonds, we're just talking about the shared bonds. Okay. Now, we've mentioned before that if you have a polar covalent bond, and I'm just going to add it up here. If you do have a polar covalent bond, which is this guy, you will have a shift in electron density. And just to reiterate, right, if I do have the hydrogen and I do have the fluorine, and I discuss where those electrons are in the bond, you tell me, right, would these electrons in the shared bond, would they be towards the hydrogen? Would they be in the middle? Or would they be towards the fluorine? You're absolutely correct. They would be right towards the fluorine, because it's always going to be towards the more electronegative element. In the term electronegativity, the word electron is in there. So it's going to attract those electrons. Okay, now let's just make a cute little symbol as to how we show this shift. And this is from the dipole moment, the shift. Now it's going to be a cute little arrow. Just know that the shift, the electron density shift, is always going to be towards the more electronegative element. So this is the more electronegative element. It's got a greater value, 4.0. So we're going to be shifting this way. But I can't just draw an arrow like this, right? It's got to be cute. So we add a little tick on this part. How cute is that? But we can determine, oh boy, I'm stuck in a loop. Oh boy. Okay. But from this cute little symbol, right, we can talk about partial charges. Keep in mind that ionic bonds are complete transfers, which means that you have direct positive and negative charges. One lost, positive, the other one gained, negative. These are still sharing electrons, so they're not direct positives and negatives, but they're partial positive and negative charges. And that's symbolized by this cute little arrow. Now, keep in mind that you will always go toward the more electronegative element. Look what I just drew. I drew a negative value in that arrowhead. So we'll say this side is always, the arrow is always going to be facing the more electronegative atom. And on the other side, there's a secret positive, which means that that side is the one that has the lesser attraction. And in this case, the positive end of your little cutesy little arrow is always the less electronegative. Okay? And from that, from drawing the arrow, you can determine now the partial positive and partial negative charges. The one that has that arrowhead that's like, the positive, that's going to be partial positive. The one that has the secret negative, that atom is going to be partial negative. How do we write that? Well, there's like this little, I think it's called epsilon, but it's this symbol right here. It's like this cute little S. Whee! The positive end has this little cute little epsilon thing with the S. Actually, I don't think this is epsilon. I think this is delta. So like delta S, delta positive, and then delta negative, right? Delta, this is lowercase delta, because you'll see like in other things like delta T, capital, it's like that triangle. But still, it means a change. So change to positive change to negative. There was a shift in the electron density. So the one that has the positive end of the arrow is the partial positive. The one that has the secret negative in there is the partial negative. And this just denotes as partial charge. So partial positive. Can't say that it's a full positive or full negative because it's not ionic. There's still a charge there. Now, if you have a certain type of pull, and you can make these little cute little partial positives and partial negatives with this type of symbol, just know that with all this included, this compound, so in this case HF, or any type of compound that would be classified as polar, that has a polar covalent bond, these would all contain dipole moments. Now, dipole moments can be calculated. I don't really necessarily think that you would have to calculate a dipole moment, but just know that the dipole moment lettering is this mu. So it's like a backwards U. And dipole moments are basically when you do have an unequal pull of these electrons and where you have negative sides and positive sides. Basically, you're not symmetrical anymore, right? You have a positive end and you have a negative end, and they're clear, right? Keep in mind that when we were talking about, nonpolar covalent bonds, where we had two H's, and I had an electronegativity difference of 0, there would be no partial positive, there would be no partial negative, because those electrons are split right down the middle. So H2 has no dipole moment. I'm just going to put up the formula here. If we need to, utilize it, but dipole moment equals a Q value, which is a charge, multiplied by, we'll say R. And R is the distance between the charges. So whether it's a positive and a negative, +1, -1, it's the distance between the charges, aka like the nuclei, right? Just putting it out there. I doubt that, usually they don't, teachers or professors, they don't whip this out. We will get into another formula probably next lesson, Coulomb's law. But you can just probably theorize this, meaning you don't really have to calculate what it is, but just know your relationships, that the higher the distance between your nuclei, your dipole moment would increase. If one of these, decreased, what would happen to the dipole moment, etc., etc. But the main thing here is that, and I'm going to put it at the bottom, is that if, and maybe we'll say, if you have a diatomic molecule, so now I'm giving you more information, right? Diatomic, di in chemistry means 2, and we have 2 atoms. We've seen 2 of these already before. If you have 2 atoms, we've seen it as H2, right? Here's 2 atoms, 1, 2. You have HF, 1, 2. So those are all different types of diatomic molecules. But if you have diatomic molecules of different atoms, this is general, that have the polar covalent bond, right? These are called polar molecules. So if you have a diatomic molecule of different atoms in which you have a polar covalent bond, that whole entire molecule would be classified as polar. The whole thing, the whole shebang. Now I know I'm running out of room here. I'll take this and I'll just rewrite it on the next page, and then we'll go from there. So let's go. Okay, so here we are again, just going between nonpolar covalent bonds and polar. We've already discussed HF, and we just said that two atoms, aka a diatomic molecule of different atoms, so it would have to be something like X and Y, right? We just have to have two different atoms. In this case, one was hydrogen and one was fluorine. If you have a polar covalent bond, which means that if you do that electronegativity difference and it's between 0.4 all the way to 1.8, you will have a polar molecule. Now, there are examples of this. HF is one of the examples. You could think about HCl, right? That would have a polar covalent bond. You could find out the electronegativity. That means that the whole entire molecule is polar. You could do carbon monoxide, CO, right? You could do NO. These are all polar molecules. But on the flip side, if you have diatomic molecules, so we'll put it on this side. If you have diatomic molecules, diatomic molecules of the same atoms, so that's for sure. And I'm going to put a big or different atoms, which I don't even know if that could be even possible, if it's diatomic. And no, because those are like, I think they go up by 5s. So I don't even think that you could even have a diatomic molecule that would be non-polar. I'm just going to put it, because knowing chemistry, there's always going to be, probably one exception. So I'm just going to add it. Diatomic molecules of the same atom or different atoms with that electronegativity difference just has to be below 0.4. Negativity difference of less than 0.4, that would be classified as a nonpolar molecule. Right? So if you have nonpolar covalent bonds, right, and you're talking about diatomics, you got a whole nonpolar molecule. So examples of this, we've seen 2 of them already. H2, we've seen F2, we've seen N2 today, and we'll add everyone's favorite O2, right? But, those are just examples. So I think that's good for that. So general nonpolar diatomic molecule versus polar diatomic polar molecule. And just know that for an overall nonpolar molecule, no pull, no dipole. And also that pull idea is there as well, right? So you could think of that pull in dipole as a pull. No dipole moment, which means no pull. You only have dipole moments in polar or ionic. But that would be a complete transfer. So I wouldn't even say that. You have a dipole moment in polar molecules. So have dipole moment. Okay. Now, this can get a little bit tricky, right? When we start branching out into more than 2 molecules, 2 atoms in a molecule. For example, what happens if we add a 3rd atom? And once again, we do not have to know how to draw these Lewis structures. Remember, Lewis structures and knowing how to draw them is coming after the fact, right? In a different lesson. But we just have to look at them and see what's going on. Now, one of the key elements, or not elements, but we've actually seen this compound before, in which we talked about carbon dioxide, right? Where we have carbon in the middle, and then we have 2 oxygens at the end. and the oxygens had 2 lone pairs for each one of them, and they had 2 bonds. Okay. Now, depending on the shape of the atom, and maybe what I'll do is I'll just, oh boy, hold on. Let's do this a little bit lower like that. Okay, yep. So we'll say this structure versus this structure of carbon dioxide. Keep in mind, they're both going to be CO2, but one of them is going to be straight, linear, and the other one is going to be a little kinked. And this, we're definitely going to get into this in great depth when we start doing geometry. But I kind of want to just get you started a little bit, right? So here's the 2 oxygens. Once again, it's still CO2, but the only difference is the shape of what it looks like. And remember, when you're talking about dipole moments, you have to have that arrow. Keep in mind that we go towards the more electronegative element, and the other end has a happy positive, right? So we have to know who's more electronegative, who's less electronegative. And electronegativity, this little shape thing, is for each individual bond. So for example, if carbon dioxide was shaped like this, and we talk about this bond, right? Doesn't matter whether it's a double, single, or triple bond. It's a bond nonetheless. It's a covalent bond because I drew it as lines. Also, if we look on the electronegativity diagram, we will see that oxygen is more electronegative than carbon. So there's a dipole here, right? The difference is going to be from 0.4 to 1.8. And since oxygen is more electronegative, we go towards that difference. And the positive one has a happy little plus. Now, if we were talking about this side, right? Here's another bond. Oxygen is more electronegative, right? So if we were talking about this bond, we're going towards oxygen and the carbon gets a little happy, right? So in this case, this oxygen is partial negative, this oxygen is partial negative, and we got basically like 2 partial positives, depending on what, what bond we're talking about. Okay. Now let's just quickly do it for this one as well. We already discussed that oxygen is the more electronegative, but in this case, we just follow the bond. So we're going down towards the oxygen, little happy plus on the other side. We're going down towards the oxygen, little happy plus on the positive side. And if I just drew it down, this would be partial negative, and then technically 2 partial positives depending on what bond you're talking about. Now, this is why shape comes into play a lot, and we're going to be talking in depth about molecular geometry, not in this lecture or lesson or discussion or just hangout session, because we've been hanging out for like, 2 hours, right? I don't even know what time it is. Past my bedtime, but we get it done, right? We love chemistry, and I love hanging out with you guys. So it's a win-win. Where was I? Oh, yeah. So this is where it comes down to knowing your geometry and knowing whether a molecule would have a dipole moment or would be classified as nonpolar or polar. Now, if CO2 was a linear shape, right? It's got 180 degrees. It's a straight line. There's no kink, right? This technically, since there's a kink, we would call this like it's bent, right? If it's linear, right, it's like a tug of war. This oxygen's tugging to the left, and this oxygen's tugging to the right. And it's the same element. So if you have the same strength on the left and the right side, linearly, is that carbon going to move? Or are any of those electrons in those bonds going to move? No, because it's fair game, right? You have an oxygen on the left, you have an oxygen on the right. So there's no pull. So would this structure, if it was linear, would this be overall nonpolar or overall polar? It would be overall nonpolar, even though we do have polar bonds. We have two totally polar bonds here. However, the overall molecule would be classified as nonpolar because everything cancels out. So nonpolar molecule with polar bonds. And that could happen. Just to show you over here, if carbon dioxide was bent, right? Would this one have a dipole moment? Would it be classified as polar or would it be classified as nonpolar? Well, the oxygen is pointing downward. It's pulling down. And the same oxygen is pulling downward, right? So overall, these oxygens are going to win. Whether one's going to the left, one's going to the right a little bit. But the idea is that they're both going down. So there is going to be a general pull towards the bottom because you don't have anything higher up to cancel it out. So if carbon dioxide was in this structure, this would be classified as a polar molecule. But I just want to show you that you can have nonpolar molecules with polar covalent bonds. This one, since they did have polar bonds, could be polar molecule. But just know that sometimes they will cancel out. Now, it turns out that CO2 doesn't exist like this. So this is out anyway. This does not exist. It is the linear form. So it does take note that sometimes you can have polar bonds, but the overall molecule can cancel out and have be nonpolar, and that means that it has no dipole moment. So you just got to watch out for that, but that comes with knowing your geometry, which comes from Lewis structures, but you're going to get into that at a much later date. So hang tight though, because, we'll be seeing that soon. Also, I just want to point out that now there are some exceptions, but another example would be NH3, right? We have nitrogen in the middle, surrounded by 3 hydrogens. We've already seen that the hydrogens, they always like to have just one bond, and nitrogen has 1 lone pair. Remember, we have a whole nother lesson on Lewis structures for you, so don't necessarily worry about how this came about. But if you see that you have a lone electron in the center in one of your elements, that means that that's going to be where the highest electron density is. So that's where your dipole moment is going to be. And it's going to be polar. Just to kind of give you a little heads up as to what we're going to be discussing moving forward. For right now, it's just the general gist of covalent bonds, covalent molecules, nonpolar bonds, nonpolar covalent molecules, and with your ionic type of idea as well. Keep in mind that it's just a continuum. Now we have finally come to the end of our journey. We got one more important thing that I want to not cram, because what are we on, hour 3 now? I have no idea. 5 minutes ago, I just said hour 2. I have no idea what time it is, but we're almost done. I want to get through one more thing that probably is going to be on a test or quiz, and then we shall depart from each other. From this video, right? But not forever. Not forever, right? And the last thing that I want to discuss is metallic crystals, or some of your teachers or professors might call it metallic solids. So I'm just going to write it up here. Metallic crystals or metallic solids. Now, this isn't necessarily a type of chemical bond, but it's just talking about a specific type of structure or crystal. Mainly because if you have an ionic, we talked about ionic compounds, which have ionic bonds in them. We talked about covalent compounds that have covalent bonds in them. So in essence, we now are talking about metallic compounds or metallic crystals or metallic solids, which, quote unquote, have metallic bonds to them. But you'll see in a little bit how these are a little bit different. Now, just know that if you have a metallic crystal or a metallic solid, the drawing of these is not the same as ionic or covalent. There are no transfer of electrons, right? So that's out. There are no sharing of electrons, that's out. I say kinda. The idea here is that when you're talking about metallic crystals or metallic solids, let's just put out the examples. Now, these are just your pure metals. So it has to be just a metal. So we're just talking about a block of sodium. We're just talking about a block of lithium. We're just talking about a block of magnesium. And because of that, I can't really say that there's any bonds in here, right? Because it's not two different atoms. It's not, NaCl or, HF like we discussed before. So when you're talking about metallic stuff, you are just talking about a metal, whatever that is. Copper, sure. Iron, sure. Doesn't matter, just got to be a metal. Now, with your metallic crystals or metallic solids, right? Since these are metals, they are going to be a solid at room temperature. And remember when we discussed about solids, they are very dense. Right? So there's a lot of stuff crunched into a block of magnesium or a block of iron or a block of whatever, right? So let's just draw the block. Keep in mind, let's just, for our case and purposes, let's just say that we got a block of, I don't know. It doesn't really matter. Let's just say we got a block of iron. So that's Fe. And since this is a solid, right? Iron is a metal, it's a solid. It's going to have tightly packed, maybe I could get 3 rows in here. 1. This is very bad. They should all be the same size. I could sit here for maybe 2 hours just trying to perfect these circles. But, you might be like, okay, bye. And I totally get it. Just know that each one of these is an iron, right? And remember, the nucleus, which is the center of all these circles, the nucleus is always positive. So we have positive, 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 positive. Can you guess it? Positive, positive, positive. So we have about 9 irons here with all positive nuclei, right? And now the question is, well, where's those electrons? Well, the electrons are, keep in mind that electrons are outside the nuclei, but they're swimming. They're swimming in the sea. And it's one big party. Basically anything that is not around the nucleus. I mean, there are some, maybe we'll just do like this. We'll say, this is probably much better. These orange circles that I'm drawing now are where the electrons live. And once I draw this, I'll highlight what I'm saying. But remember, electrons live outside the nuclei. So that, and we'll give 2 examples, 1, 2, and maybe 3, right? All these orange, this is where the electrons live. But now, if you noticed, when I drew it, it becomes like almost a single unit, right? Where electrons can easily, maybe I'll do this in purple, electrons can easily just flow in and flow around because the metals are so tightly packed that these are called delocalized electrons. So now we're talking about something completely different. So if we're talking about chemical bonds and they talk about something called delocalized, which we have not discussed, this is purely all about your metallic solids. You have something called delocalized electrons. Now, if something is delocalized, D like without, not. Delocalized electrons means that the electrons are not, guys, it's hour 3. These electrons are not, sorry, these electrons are not local, right? And where's that from? By the way, I have to say it, right? If I did a good job, let me know in the comments where that's from. So these electrons are not local. Usually, like if you have like a local rash, that rash is only on one specific part of the body. But if electrons are not local, that means that they can roam. They are free to roam around, and they are not just this iron's electrons. They're not just this iron's electrons. These electrons can swim, and they can travel, and they can visit their friends because they're delocalized. They are not bound to one specific element, one specific iron. They're going from one iron to the next. And that's why these bonding electrons are very unique, because they have this idea where it's flowing. They say that for metallic solids or metallic crystals, that there are positive ions, which are the positive nuclei, right? The iron. So it's the positive ions that we could say that are submerged or immersed, right? Or put in, whatever you want to say, in a, and this is usually the wording that they would use, a sea, like an ocean. A sea of delocalized electrons. Because those electrons are swimming. Elements, God. Electrons. So yeah, sea like an ocean. An ocean of electrons. They're just swimming around. They're not one specific irons. They're everyone's iron. They're delocalized electrons. And because of this, this has great implications for its properties. So because these ions, or, these positive ions can be exposed because the electrons are swimming around, right? Electrons are negative. So you have like clearly positive and clearly negative parts of the metal. This makes the metallic solids great conductors of heat and electricity. So great conductors of heat and electricity, right? If you put like a metal spoon in a pot of boiling water and you keep it in there, you're going to burn your hand off because they're going to absorb all that heat. It's because of the sea, the ocean of the electrons, the delocalized electrons. Great conductors of heat and electricity. I think for that, that's pretty good. Usually they're great conductors of electricity. Depending on the metal, you could have a range of melting points. So you could have like low melting points, high melting points. They come in all different shapes of sizes because now you're expanding it to all different types of metals, whether it's alkali, alkaline earth, your transition metals. So they could be brittle to extremely, extremely hard. But the idea here is that when you're talking about the metallic solids, It's that idea of the swimming electrons. So you're exposing the positive and the negatives. And if anything, the type of chemical bond this would have would be a metallic bond. It's not a bond that we know it as because there's no sharing, there's no pull, there's no transfer of electrons. It's this idea of free-floating, swimming electrons with the positive metal. And I think after our whatever, we have made it to the end. I am so excited. So, guys, that's a wrap on today's lesson. All about types of chemical bonds. I mean, we hit it. We hit it even with the kitchen sink, right? We took the kitchen sink. We included it in there. There is nothing that was not included that's going to be on a test or quiz in this, discussion or lecture. So next time, I think what I got going on for you in the next lesson, we are going to be basically talking about more of electrons, yay, but with graphs. So we're going to see a very famous potential energy graph. So we'll check into that. That one shouldn't be as long because it's more specific. This one we had to do ionic, we had to do covalent, we had to do metallic. So that's good with that. So watch out for the next lesson. But I have to say, before you go, since all this stuff is fresh in your brain, it's a great idea. After hour 3, come on, give me some more, right? Let's do some practice problems. And we've got tons of them waiting for you at lasersguide.com to help you master types of chemical bonds. So let's go. The link is in the description and at the end of the video. So you could go on now. You can, click on over. And remember, for more practice and for more fun, head on over to glazersguide.com. See you there, and I hope you have a great, great day. Bye-bye.
For more practice and for more fun, go to glazersguide.com.
And for more practice and for more fun, come on, go to glazersguide.com.